In this video, we're going to look at ways we can evaluate the integral of a rational function. And so this is done with method of partial fractions. All right, so first, remember, rational function is any function of the form p of x over q of x, where p of x and q of x are both polynomials. Right now, we call f proper if the degree of the numerator, in this case p of x, is less than the degree of the denominator, right? The rational function is said to be improper when the degree of the numerator is greater than or equal to the degree of the denominator. So the first thing we want to do, whenever we see a rational function, we want to make it proper. Then we will proceed from there. When writing a rational function and its partial fraction decomposition, right, we have four possibilities. We first look at what happens if we get in the denominator, right? So in other words, we have f of x equals p of x over q of x, right? What happens? Q of x has ax plus b as a factor. In other words, we're looking at the distinct linear factors. Well, in this case, the factor ax plus b contributes a over ax plus b to the decomposition. Now, what if q of x has ax plus b to the r as a factor? Right, in other words, this is a repeated linear factor. Well, in this case, we get the contribution a1 over ax plus b plus a2 over ax plus b squared plus so on and so forth plus a sub r over ax plus b to the r to the decomposition. Now we look at what happens if q of x has ax squared plus bx plus c, where this is irreducible, as a factor. Right? In other words, we consider a distinct quadratic factor. So this factor contributes ax plus b over ax squared plus bx plus c to the decomposition. Final possibility is q of x has ax squared plus bx plus c raised to the rth power as a factor. This is a repeated quadratic factor. In this case, we get a1x plus b1 over ax squared plus bx plus c plus a2x plus b sub 2 over ax squared plus bx plus c squared plus so on and so forth plus a sub rx plus b sub r over ax squared plus bx plus c raised to the rth power to the decomposition. We will now look at several examples of antiderivatives of rational functions. Let's first look at the antiderivative of x squared plus 3x plus 5 all over x plus 1. Right, the first thing we want to do is make this proper, right? So this is currently not proper. So to make it proper, we do polynomial long division. What do we multiply x by to get x squared? Well, that's just simply an x. All right, now we just subtract the 2. So we get 0. 3x minus x is 2x. That 5 drops down. What do we have to multiply x by to get 2x? Well, that's just 2. All right, subtract them. 5 minus 2 is 3. So what we get is the antiderivative of x plus 2 plus 3 over x plus 1. Well, the antiderivative of x is simple. That's x squared over 2. Antiderivative of 2 is simple. That's just 2x. Antiderivative of 3 over x plus 1. Well, that's just 3 times the natural log of the absolute value of x plus 1. Right, and then plus a constant. So in this case, all we had to do was make it a proper rational function, and we got an antiderivative straight away. There was no need to write a partial fraction decomposition. For our next example, let's look at the antiderivative of 3x plus 2 over x cubed minus x squared minus 2x. Now this is already proper, so there's nothing else to be done. Now let's do partial fraction decomposition. First thing that we want to do is completely factor the denominator. Where we can factor out an x. Now x squared minus x minus 2, this can be factored to x plus 1 times x minus 2. Now we can start to write our partial fraction decomposition. We have three distinct linear factors. The first linear factor is x, so we get an a over x. Second is x plus 1, so we get a b over x plus 1. And finally, it's x minus 2, so we get c over x minus 2. Our goal is to now find the a, the b, and the c. All right? Well, clear out denominators. In other words, we're going to multiply both sides of this equality by this denominator, this x times x plus 1 times x minus 2. What we are left with, 3x plus 2 is equal to a times x plus 1 times x minus 2 plus b times x minus 2 plus c times x plus 1. All right, now expand everything out. X squared minus x minus 2 plus b times x squared minus 2x plus c times x squared plus x. Let's now gather together like terms. So for x squared, we're going to have an a plus b plus c. For x, we have a negative a minus 2b plus c. And finally, in terms of constants, we just have a negative 2a. Now what we do is a technique known as coefficient comparison. Right? In other words, what's the coefficient of x squared on the left-hand side? It is 0. Coefficient on the right-hand side is a plus b plus c. So what we have to have is a plus b plus c has to be 0. Right? Compare the x's. Negative a minus 2b plus c has to be 3. And finally, negative 2a has to equal negative 2. Right? So this is a system of 3 equations and 3 unknowns. We wish to solve this. Actually, that should be positive 2, right? Negative 2a equals positive 2. Right, so, solving a system of equations. Easiest thing to do is to use a calculator, a computer algebra system. So let's go over. So what we want to do is we want to go to Menu, Algebra. We want to come down, 7, solve system of equations, and solve a system of linear equations. It's then going to ask for the number of equations. Well, this one we have 3. Hit Tab. And then what variables? We're using A, B, and C. So A, B, C. Hit Enter. Now we just enter the 3 equations. All right. So what did we have? We had a plus b plus c is equal to 0. We then had negative a minus 2b plus c was equal to 3. And then finally we had, well, negative 2a is equal to 2. Now just hit Enter. And the solution is a is equal to negative 1, b is equal to negative 1/3, and c is equal to 4/3. So what we have now done is we've said, look, this antiderivative is now equal to the antiderivative of negative 1 over x minus 1/3. Let's do it this way. minus a third over x plus 1, then plus 4 thirds over x minus 2. We can now evaluate each of these individually. We get negative log absolute value of x minus a third log absolute value of x plus 1 plus 4 thirds natural log absolute value x minus 2, and then plus a constant. And so this is our antiderivative. For our third example, let's look. Antiderivative of x minus 2 over the quantity 2x minus 1 squared times x minus 1. So the degree of the numerator is 1. The degree of the denominator in this case is 3. So we are in proper fraction form. So we just need to write it in its partial fraction decomposition. Right, so 2x minus 1 squared, that is a repeated linear factor. So it'll contribute a over 2x minus 1 plus b over the quantity of 2x minus 1 squared to the decomposition. Right, x minus 1 is a single distinct linear factor. So that'll contribute c over x minus 1. Now again, let's go ahead and clear out our fractions. So x minus 2 is going to equal a times 2x minus 1 times x minus 1 plus b times x minus 1 plus c times 2x minus 1 quantity squared. Now again, all we did was multiply both sides of the equation by the denominator 2x minus 1 quantity squared times x minus 1. So we get a times 2x squared minus 3x plus 1 plus b times x minus 1, nothing to do there, plus c times, now let's expand that, 4x squared minus 4x plus 1. Let's once again form our, group together like terms. 2a plus 4c x squared plus negative 3a plus b minus 4c times x plus a minus b plus c. This gives us our system of equations. 2a plus 4c has to equal 0. Negative 3a plus b minus 4c has to equal 1. And finally, a minus b plus c has to equal negative 2. Once again, we're doing coefficient comparison. All right, so let's go ahead and come over to our CAS. I hit the wrong one. And again, we have three equations, A, B, and C. Right, so the first equation, 2a plus 4c was equal to 0. Second equation, negative 3a plus b minus 4c was equal to 1. Final equation, a minus b plus c is equal to negative 2. Let's solve that. We get a is 2, b is 3, and c is negative 1. All right, so what we can do is now write our antiderivative as the antiderivative of 2 over 2x minus 1 plus 3 over 2x minus 1 squared minus 1 over x minus 1. First antiderivative will be natural log absolute value of 2x minus 1. That's not going to be a plus, it's going to be a minus, right? Minus a 3/2 times 2x minus 1 to the minus 1 power. And then minus natural log of the absolute value of x minus 1 plus a constant. And we can simplify this. Natural log of the absolute value of 2x minus 1 over x minus 1 minus 3 over 2 times 2x minus 1 plus a constant. Now let's take a look. Antiderivative, 2x minus 3 over x cubed plus x. Again, this is already proper. So let's completely factor the denominator. We'll have 2x minus 3 over x times x squared plus 1. Right, that is fully factored. Right, well, we have the linear factor x, and it's distinct, so that contributes a over x. Then we have a distinct quadratic x squared plus 1. So that factor contributes bx plus c all over x squared plus 1. Now we will continue in much the same manner. Clear out fractions. We'll have 2x minus 3 is equal a times x squared plus 1 plus bx plus c all times x. Okay. Distribute the x through. Now let's group together like terms. We have a plus b times x squared plus c times x plus just a. Now coefficient comparison, we're going to get a plus b has to be 0, c has to be 2, and a has to be negative 3. Now this doesn't require use of a CAS. This is a very simple system to solve. We're already told that a has to be negative 3. We're told that c has to be 2. So negative 3 plus what is 0? Well, that's 3. So we get b has to be 3. So we rewrite the antiderivative. Now is the antiderivative negative 3 over x plus, then we have this, 3x plus 2 over x squared plus 1. Now what we're going to do is actually write this as 3 fractions. So we get negative 3 over x, then we get plus 3x over x squared plus 1, then we get plus 2 over x squared plus 1. Get negative 3 log absolute value of x plus 3/2 natural log absolute value of x squared plus 1. That is a simple u sub. Plus 2 times the inverse tangent of x plus our constant. And finally, let's consider the antiderivative of 4 minus x over x times x squared plus 2 squared. This is already proper. So we now write out its decomposition. We have a distinct linear factor x, so that's a over x. Now we have a repeated quadratic. So we have bx plus c over x squared plus 2, then plus dx plus e over x squared plus 2 squared. And now to proceed, same fashion. Clear out the fractions. We get 4 minus x is equal a times x squared plus 2 squared. Plus, now we get bx plus c times x squared plus 2. Plus dx plus e times x. Let's go ahead and expand stuff out. Group together all of our like terms. And now use coefficient comparison. Right, so a plus b must be 0. 4a plus 2b, I'm sorry, I skipped one. C has to be 0. 4a plus 2b plus d has to be 0. 2c plus e has to be negative 1. And finally, 4a has to be 4. Again, this is a fairly straightforward system to solve. Right? We know that a has to be 1, which means b has to be negative 1. We know that c is 0. Right? Plugging the known values in, we find that d is negative 2. And e itself is negative 1. So this antiderivative can now be rewritten. One over x minus x over x squared plus 2 minus 2x over x squared plus 2 squared minus 1 over x squared plus 2 quantity squared. The first three are simple. Right? Natural log of absolute value of x minus 1/2 natural log absolute value of x squared plus 2. Right? Then it should be plus 1 over x squared plus 2 squared. Right? But now this final one is going to require the use of trigonometric substitution. So let's look at this piece individually. Right? What we're going to do is x is the square root of 2 times tangent of theta, which makes dx the square root of 2 times secant squared of theta d theta. And the square root of x squared plus 2 is square root of 2 times secant of theta. So here's our substitution. What we now get is the antiderivative of 1 over root 2 secant of theta all raised to the 4th power times the square root of 2 secant squared theta d theta. So we get root 2 over 4 times the antiderivative of secant squared over secant to the 4th, which is 1 over secant squared of theta d theta. Which is root 2 over 4 antiderivative of cosine squared theta d theta. That's root 2 over 8 antiderivative 1 plus cosine 2 theta d theta. Root 2 over 8 times the quantity of theta plus a half sine 2 theta. So root 2 over 8 times theta plus root 2 over 8 sine of theta cosine of theta. Right, because remember, half sine of 2 theta is sine theta cosine theta. Okay. How do we want to convert this back to x? So we know we're going to have root 2 over 8 inverse tangent of x over root 2 plus root 2 over 8 times. Now we need to write sine and cosine in terms of x. Well, let's take a look at our triangle. There's theta. Tangent was x over root 2. Right, so hypotenuse is square root of x squared plus 2. Right, so sine would be x over square root of x squared plus 2. Cosine would then be square root of 2 over square root of x squared plus 2. So we get root 2 over 8 inverse tangent x over root 2 plus x over 4 times x squared plus 2. Therefore, we can now write our antiderivative, which was log absolute value of x minus a half log absolute value of x squared plus 2 plus 1 over x squared plus 2 plus root 2 over 8 inverse tangent x over root 2 plus x over 4 times x squared plus 2. Plus our constant. We could simplify this log absolute value of x minus a half log absolute value of x squared plus 2 plus root 2 over 8 inverse tangent of x over root 2 plus 4 plus x all over 4 times x squared plus 2 plus a constant.